right? The hydrocarbon has a shape of hexagon, and then these two hydrogens, we can put it there. So one carbon has carbon to carbon and hydrogen to hydrogen. So, but this doesn't show 109 tetrahedral for all sigma bonds. It doesn't show in this one, right? So what we're going to do, we're going to draw a left tip and a right tip on the hexagon, and then shade like an envelope here in red, and that's the one carbon, and then 2, 3, 4, 5, 6, you number it, and then you're going to draw 1 to 2 looking up. So because we're going to push that up. And then the green shade area, 5, 4, 6, should be looking down. So the fourth carbon is looking down actually. So 5 to 4, right? Now we're going to connect them. So this is pushing up 1, and then we're going to connect them, the fourth carbon down, right? And then we're going to connect them just similar to the Nike sign or check mark and the inverted check mark 2 to 4. So now you can put the numbering correct, right? And then flip the ring. So this is not an alligator rolling, right? This is a tip up and down. So now in this case, carbon 1 should look down after the flip, and then carbon 4 should look up. So that's what I did. So you can stop the video and practice a couple of times to do this, and this is the most important thing to do. Now, so we're gonna move to yes, let's look at this hydrogen here. So at the fourth carbon, these two hydrogens looks like tetrahedral 109 now, right? See, then you have to see what is coming towards you, what is going away from you, what is on the paper. So now you can prove 109 bond angle, solid wedge coming to your face, and the dashed wedge going away from you. So all the carbons looking like that. That's why the cyclohexane has these chair conformations in real structure, right? So not a simple flat hexagon. So let's learn something else. So on the earth we kind of have the north and south pole. Let's mark north pole. So if I draw a cyclohexane chair conformation and then flip it 1 and 4th carbon and flip them and draw it, right? And then I should have first one and third one and fifth one should have a hydrogen to the north pole, and then there should be a 3 to the south pole. What are they? 2, 4, and 6. So those are called the axial, right? So 1, 3, 5 goes up, and 2, 4, 6 goes down. Those are axial. Not only axial, the horizontal ones are called the equatorial. So these are at 1, 2, this actually is simply horizontal. So first draw the vertical and then you do the horizontal ones, right? So how do you draw them a little bit better way? So 1 to 2 parallel to the 6 carbon equatorial likewise. So let's do another ring here. Okay, then after the chair flip, so you will get that one. So the fourth gone up and the number 1 came down, right? So now here is the fourth axial becomes equatorial. Fourth axial hydrogen after the flip becomes equatorial. Look at this green equatorial on the fifth. Okay, no, probably we should look at the fourth one. Let's see here. So the fourth one has a green equatorial. It will look at looking up, vertical, straight up. So that's an axial. So that means all axial becomes equatorial, and then the whole equatorial becomes axial after the ring flip. So that's the important thing to know. Okay, now let's look at a simpler version actually. So you can draw and practice all axials and equatorials after the ring flip it's changing. Let's look at these two. If I kind of give X and Y into the first carbon, and then so we can see what happens. You see Y downward, equatorial becomes Y downward axial. So that means whatever down gonna stay down. They only flip axial and equatorial. Up never go to down, or down never go to up, right? So let's do a good example. Okay, so here I have hydroxyl group equatorial position on the first carbon, and the fourth carbon I'm going to put a third butyl group. That's a bulky group, right? Much larger. Well, it's too little here, but you understand that. So there's 4 carbons. It's a tetra, yes, third butyl group, right? Okay. Now, after the ring flip, equatorial becomes axial hydroxyl, and equatorial third butyl becomes axial third butyl. Okay. So equatorial becomes axial, and that's what happened. So on your right side, both are axial now, right? Okay, let's look at another thing. Now here, axial hydroxyl and 1, 2, 3, third position hydrogen are kind of loggerheaded. It's called the 1,3 diaxial interaction. So that's a sort of a steric clash, you see. Look at this. On this hydrogen, and the third butyl group has a massive steric clash. It's massive. So therefore, it pushed the equilibrium to the reactant side, and you have to indicate that on an equilibrium arrow, right? Okay, so that's why the more stable form is on your left, because both are equatorial, which is good. And then we're going to look this cyclohexane ring from here, from the top view. So all I see is a hexagon when I look in from the top, because I am not clear about the depth, right? And then this OH is away from my eye, so it's a dashed wedge. And this third butyl group is coming towards my eye. It's sticking up like a flag. So that should be solid wedge. So that's how you differentiate or in the line diagrams, right? So third butyl coming up and the hydroxyl going down. Another thing you can notice here. So these compounds are also called the substituents, right? How do you see that? Look at this double bond. This is a trans compound, right? Now, if you look at the cyclohexane, they have up and down. So double bond and the cyclohexane ring, a little bit similar. So you can think that way. So this is a trans compound. Now, so yeah, we can talk about the energy and the dihedral angle or the torsional angle, right? This is also related to exactly the math. Delta G is negative RTL and KEQ. KEQ is the productive reactance, right? We can actually do the free energy calculation, but we're just going to look at qualitatively. Okay, just the picture. So the delta G and torsional angle versus delta G against the delta G, we can plot 3, right? So this 3 will kind of give you a good comparison. So let's see here, this is for ethane, and it would be like a wave. So there's a, and then I kind of say this is a happy monster for butane, and that's a hydrocarbon, right, for the butane. And then ethane will have a wave, butane will have a happy monster in the energy diagram, and cyclohexane will have a angry monster, I say. Angry monster, but it well, it has actually a crown, right, or on the head. It's a boat, actually. He's keeping a boat on the head. Maybe it's heavy, it's getting angry, right? Okay, so let's see. So now we can say this starting point is 1C4 for the cyclohexane. The other one is 4C1. So they are the equal things, and you already draw them. You can redraw on the graph just to get the idea about the energy. So let's look at the simpler one, ethane. So the ethane, we know there's 2 prominent ones. That is, one thing is the staggered form, all spread perfectly, and the other one is the eclipsed version. In this one, how do you do it? So you draw always the back circle one and then push the top dot one like a steering wheel, right? You rotate the steering wheel in a one direction in a way. So now you get the eclipsed version that should have the more steric interference, right? So that will have high energy. Look at this one here. The happy monster is on the head of the happy monster, actually all eclipsed. It's very high energy. Maybe that's why it's happy, right? So if you have a model, build it and flip it and see what happens. You start with this one. So it's a 1C4 cyclohexane, and then open one end, it's called the half chair. Then there's a twisted chair. It's very hard to kind of explain. That has the highest energy, actually. Twisted energy, right? And then in the head of the monster, that's the boat, has high energy relatively too. But this has a unique one. These two hydrogens are called the flagpole interaction, or flagpole effect, actually. So it pushes each other, so it has high energy. So the lowest energy is A, and these behaviors of these three graphs are harmonical, so they kind of repeat.